Okay, welcome all. This is a TCS seminar at the Agilent University. Today our guest is Freddie Illingworth from London, University College London. Freddie did his PhD in Cambridge in 2022, one. Okay, so 4 years after PhD. Freddie worked at Oxford with Alex Scott, and now you are a postdoctoral researcher or
research fellow.
Research fellow. So you're more in the structural graph theory or extremal graph theory?
I have papers in both.
Okay.
This is more extremal, but I'll hopefully make it interesting for people.
So we're happy to have you here. The floor is yours.
Thank you very much, everyone, for coming. Please interrupt me, ask questions if I don't make sense. I'm talking about joint work with Francesco Di Braccio, who's a PhD student at LSE, so the London School of Economics. It's about Zarankiewicz problems in tripartite graphs. So it's a bit more extremal than maybe what you're used to. So let me just mention a couple of extremal results that I think you will know. So everyone knows Mantel's theorem. So if I have a graph G with n vertices, and I'm going to give it in the minimum degree form. So if the minimum degree of G is at least n over 2 plus 1, we know G contains a triangle. And this is very easy, right? You just take two vertices, U and V, that are adjacent, look at their common neighbourhoods, and there isn't enough space for their common neighbourhoods to be disjoint, so they overlap, and that gives you a triangle. Okay. Possibly less. Well, I'm sure many of you know this, but certainly less trivial. So the sort of Zarankiewicz problem. So I think Zarankiewicz was the University of Wrocław.
Oh.
Yeah.
More before war?
Before. Well, the Kővári-Sós-Turán theorem. So what does this say? So now we have a graph G which has n vertices in each part, and it's bipartite, and the theorem says if you have minimum degree more than n to the 1 minus 1 over t, you have a complete bipartite graph with t vertices on each side. So you can find t vertices here, t vertices here, and you have all edges between those t vertices. And what's the proof of this? Well, the proof of this is also relatively simple. You just count stars. So you count collections of one vertex on the left and two vertices on the right that are complete. And if the minimum degree is big enough, you'll find that there have to be t vertices on the right that lie in t different stars, so that you get each of the two vertices on the left dominating them. Now, right, Mantel's theorem is tight, like complete bipartite graph, but is this tight? So do we need this? Is this the right power? And the answer is for the t equals 2 and t equals 3, yes, they're tight. And t equals 2 is this projector plane, lines and points incidence. T equals 3 is another geometric construction, slightly less trivial. And t is 4, it's open. But people believe it's true, and there's people. We just haven't yet found the right geometric or algebraic construction.
So this is n to the power 1 minus 1 over t?
Yes. Yeah, so for t equals 2, it's root n.
Okay.
Yeah. Okay, good. So these are sort of typical extremal type theorems with some minimum degree guaranteeing you some structure appears. And motivated by these, in 1975, Bollobás, Erdős, and Szemerédi asked, okay, so this was for bipartite graphs. What about for tripartite and multipartite graphs? So now I have a tripartite graph, n vertices in each part, and this is G. And okay, what's the most basic thing you can ask? Well, you could ask what minimum degree, right, implies you have, let's say, KTTT. So I want T vertices and so what is the right thing to put there? Okay, so let's just, baby case, T equals 1. So that's just asking what minimum degree gives me a triangle. And they showed and I'll give you a proof of this later. So this is not as trivial. The proof is not as trivial as Mantel, but it's cute. And so if you're bored, think about it. I'll give you a proof later.
So what is n?
N, sorry. Number of vertices in each block.
And what is that the same as t?
No, sorry. So here, you had a big graph G with n vertices here and n vertices here.
Yeah. And
you're looking to find a KTT.
Okay, yeah.
Right, this KT is some fixed number you're looking for, and n is the number of vertices. Well, okay, 2n is the number of vertices in your graph.
Yeah.
Thank you. Yeah. Throughout n will be the size of each of these parts, the size n, and you're asking what minimum degree guarantees you find some structure.
So you already have this partition, and you're trying to find it relative to this given partition.
Sure. Yeah. Or your edges. It's a tripartite graph, so you don't have edges inside the parts.
Yeah.
You have edges between parts. Yeah. So yeah, this is a tripartite, and this here was bipartite. Yeah. Very good. Okay. So this right. So I'll show you a proof of this later. And is this tight? Yes. So here are a couple of examples. So one example is put all edges between parts 1 and 2 and between parts 2 and 3, and then what edges? It's a sort of silly example, but there can't be any triangles because there are no edges here, and every vertex is adjacent to at least n vertices. And in fact, the vertices here have 2n neighbours. That's one example. Here's another example. So split your parts into 2 pieces, and then draw of equal size, and then draw a 6 cycle. So, right, so that's maybe not the best drawing. So what I've drawn here is a 6 cycle, and again there are no triangles, and each vertex has n neighbours. So this n plus 1 is necessary. So the question they asked is, right, fix a positive integer t, what tau guarantees the following? Sorry. So what is the smallest tau such that if G is like this graph, so n by n by n, tripartite. And its minimum degree is more than n plus tau, does that guarantee you can find KTT inside G? And we've just seen, right, so the answer for t equals 1, right, the answer is tau is 1. Tau, here tau does not depend upon n, but it will for larger t, just sort of, here this does depend upon n. So yeah, tau is allowed to be a function of n. Right. So, they proved a couple of things. So, okay, lower bound. Well, looking at this construction, it's pretty easy to adapt it. So this had no triangles. I want to add a few more edges, but still have no KTTT. So here's a construction. So all edges, just like that. And then add some edges here. And make sure this graph has no KTT. Right. If we do this, then this graph G will have no, you can check, will have no, you won't be able to find T versus T versus T versus all adjacent because there's no, you can't even find T here, all adjacent. And what minimum degree can we get? So we've added these edges to try and push the minimum degree up, trying to prove a lower bound. And what is the minimum degree here? Well, we want to put here a graph with no KTT and a large minimum degree. So that's just the Zarankiewicz problem. So for t is 2 and 3, we know exactly the right answer. 2 and 3. And for larger t, conjecturally, you would think, so if t is 2 and 3, we can definitely do this. And then I'll write, for larger t, everyone believes we can do this. So sort of lower bound is tau is, so this is my omega, so this is at least a constant times n to the power of 1 minus 1 over 2. Right, so conjecturally, and certainly for 2 and 3, this is definitely a lower bound.
So this tight on the left border means tight up to multiplication.
Oh, the multiplicative constant, yes. You care about the dependence upon n first.
But do we actually know the constant? For example, for t equal to 2?
Yes.
Because this also looks like quite basic
Yeah.
question.
So we know the constant here. And we also know the constant here, although this is less trivial. So this is tight, like the Kővári-Sós-Turán proof. Matches here, Freddie had to give a separate, slightly cleverer proof than Kővári-Sós-Turán to pull the constant out. So we do actually know the multiplicative constant for both this and this. Yes. But yeah, for these guys, any, I mean, just getting the same growth rate is the game. Right, so that's the lower bound. And the upper bound they proved was tau is big O. Right, so quite a long way away from this. So just for t equals 2, just so you can compare numbers. This is root n, well, the upper bound is 11 over 12. Okay. This was the initial. Then a bit later, Bavkar and Zhao did, well, sort of did the following. So they gave another construction. So sort of this construction is
upper bound. Some result or
that's the original paper. Bollobás and Szemerédi proved this upper bound. Yeah.
okay.
So Balco and Zhao, they found another construction. So another different to this. And what does it look like? This is worth seeing. So take your parts, keep one of them as it is, and the other one you split up, and put all the edges in a 5 cycle, and then add. So if you look at this right now, every vertex has quite big. So vertices in here have degree 4/3 n, so much bigger than n. Similarly, vertices here have a nice big degree. Unfortunately, these guys only have degree n, so we need to add some more edges. And again, you add edges here, and you add edges here. So we like big moral. You started with a 5 cycle, which has no triangle. You've blown it up in a not particularly clever way, and then you've added some extra edges to push your minimum degree up. And when you add the edges, you keep it KTT free, because that will stop there being. You can't have a TTT because you can't even get TT. So this it matches the same lower bound. It's just another construction. And they gave another proof, a different proof of this. The same, so different methods, exactly the same. So upper bound, different proof, but the same. So no improvement. Then the authors. Chen here. Luo, Ma, and Zhao. They gave another construction. So this was based upon a 5 cycle. I won't draw the new one, but it's based upon a blown up 6 cycle. It's a bit more complicated. And they improved the upper bound. So they showed so now rather than 1/3t squared, 1 roughly t squared. And it's still, just so you see the numbers, for t equals 2. So, what do we do? Firstly, lower bound, we find infinitely many more constructions. So these are just we find like a infinite family of very different constructions. And we show the conjectured tight bound. So we get exactly the bound that. So it's tight for t is 2 and 3. It's definitely tight because we have the Zarankiewicz constructions. But for bigger t, it's assuming that there are these constructions that everyone believes there are. It's tight. Up to the multiplicative constant of that, of course, but yeah. The growth rate in n is correct. Great. So what to say first? So the reason we sort of, in extremal combinatorics, part of the reason you care about extremal constructions is If there aren't very many of them, you can try and show your graph is close to 1 and use stability. But if there are lots of them, that's a bit scary. So let me just show you some of these constructions. So if you look at this, if we just sort of look at this construction, what was important? We have this graph, we had the 5 cycle. So we had the 5 cycle, and then we blew it up and added some edges. But what were the key features of the 5 cycle? The important facts, the important properties is 1, the 5 cycle does not contain a triangle. If you contain a triangle, when you blow it up, you'll get a KTTT, so that's good. Property 2, you definitely need is it's 3 colorable. So I can actually fit it into a tripartite graph. If it had chromatic number 4, I wouldn't be able to fit it in. The other property you need, that's sort of important, is its minimum degree is more than 1/3 the number of vertices. If you sort of look at this picture, there are 3n vertices, and you're aiming for every vertex to have degree a bit more than n. So you want your graphs to have nice big minimum degree, and then you weight it. So these were the properties, in some sense, that made the 5 cycle work in this construction. So if we're going to find more constructions, you should just find more graphs with these properties. But fortunately, there's a very nice theorem, that there is a family of graphs which are the graphs with these properties. Right, so these are the unidentified graphs. So let me say again, these graphs, they'll have no triangle, they'll be 3 colorable, and they'll have this minimum degree. So their minimum degree is more than 1/3 the number of vertices. And it's actually a theorem of Chen, Jin, and Kuo from the mid-90s. These are the unique graphs with this property. So any graph with no triangle, 3 colorable, and this minimum degree is a subgraph of a blow-up of one of these. So it's homomorphic to one of these. So this is a very nice theorem. What do these graphs look like? So they have 3k minus 1 vertices, and so k is an integer. Arrange these on a circle. So the circle is not the edges, you're just arranging them. And each vertex, join it to the k vertices opposite. So this is a very nice graph. It's a Cayley graph. It's vertex transitive, and just so you see it in action once, you take k equals 2, you put 5 vertices on a circle, and you join each vertex to the 2 opposite, and that's a 5 cycle. So to get our constructions, you get one of these, you blow it up, you have to weight it quite carefully, and then you add extra edges. So I won't say exactly how you weight it and so forth, but hopefully you can believe that, given one of these graphs with these nice properties, you can blow it up, add edges, and you get a graph where every vertex has degree at least n plus, or at least n, then you add a few extra edges to make it n plus n for 1 minus 1 over t, where the extra edges are these red edges, these sort of red dashes I've put in. Are there any questions on the construction?
How difficult it is to prove this? That's the graphs.
So these are the only graphs.
Yeah.
It's a bit of work. Yeah, it's not that. If you strengthen the third, make the third a bit bigger, it's easier. Right. But
means what,
well, okay, so very easy. So nice. Unjustified Erdős theorem. If your graph is triangle free with minimum degree more than 2/5, then you're bipartite. And the 5 cycle is the first thing that stops that.
Okay.
And you can show if it's more than 3/8, it's pretty easy to show it has to look like a 5 cycle. 3/8 is the point where you get the next. So if k is 3, you get an 8 vertex graph. You get the Wagner graph. But this is the if you forbid Wagner? Mobius ladder, 8 vertices. You know this because it's in. What the graph for? It's an excluded minor for Wagner. So that's the next one. That's for k equals 3. Excluded minor for k4. No. You build k4 minor for graphs. No, you build k5 minor for graphs from this, and yeah. So that's the next one in the sequence.
So you can click some Wagner graphs and planar graphs with K5 minor.
Yeah. Yeah. So they're nice. They're nice graphs. Great. Okay, so now let me talk a bit about how you prove this sort of upper bound. What do I talk about? Yeah, so I'll remind you we have a graph G, which is n by n by n tripartite, and it has a minimum degree at least n plus tau, where tau is in constant times. That'll be eventually. And we want to show the graph G contains TTT all complete to each other. So let me start just with the t equals 1 that I said was a nice little proof. And now tau is just 1. And so I just want minimum degree more than n plus 1, and I show you there's a triangle. So it's quite convenient. We have this graph G, and it's convenient to orient it. So just view it in a clockwise direction. So every vertex, I'll view its neighbours over here. This is vertex V. There'll be its forward neighbourhood, and the number of forward neighbours will be the forward degree, and vertices here will be its backward neighbourhoods. Its backward degree. So, okay, how do we prove this? Very simple. So pick a vertex U such that its forward degree is smallest. Okay, so amongst all the vertices in the graph, I'll pick one where the forward degree is the smallest possible. So here's U. Now the graph has minimum degree at least n plus 1. So U has a neighbour in the next part. Because there are only n vertices here, it has to have a neighbour in the next part. So we've got a neighbour in V. And now, so let's now think about the neighbours of U and V in the third part. So how many neighbours does U have here? U has its backward degree. Right? These are its backward neighbours. The number of neighbours it has is its backward degree. How many neighbours does V have here? It's forward degree, but U has at least n plus 1 neighbours, so its forward degree plus its backward degree is at least n plus 1. So its backward degree is at least n plus 1 minus its forward degree. But now, we picked U so that this was minimal, so the forward degree of V is at least the forward degree of U. So that's at least n plus 1. And great, that means these are two sets lying inside a set size M, they have to intersect. And there's our triangle. So this implies we have a common neighbour. Okay, so what really happened here? The important thing was that V had the forward degree, at least forward degree of U. So it'll be useful to define, so an edge UV will be a booster. It's a booster edge. If it's a forward edge, so U is in one part, V is in the next part, and the forward degree of V is at least the forward degree of U. And what this proof gave us is that if UV is a booster, then the number of common neighbours, or we have some common neighbours, how many do they have? They have at least tau. So here, tau is 1, so they have at least one common neighbour. If you run through the same argument, they have at least tau common neighbours. So these booster edges, they're good. They give you lots of triangles. So they give you tau triangles. Great. So now let's think about, okay, so Bollobás and Szemerédi, let's talk about their strategy. And their strategy was, so step 1, show that there are at least tau cubed booster edges. And once you've got tau cubed booster edges, that means you get lots and lots of, sorry, at least tau squared booster edges. That implies at least tau cubed triangles. And if you have lots of triangles, like really lots and lots, so close to, how many triangles can you have in total? N cubed is the most you can have. If you have sort of n to the 11 over 4, so just less than n cubed, then that is enough to force also KTTT. If you have lots and lots, provided T is big enough, so you just get lots of triangles, and then there are standard counting arguments to get you actual KTTT. Okay, so how does one show there are lots of boosters? This is quite pretty. So the starting graph has 3n vertices. So I'll order my vertices, v1, v2, label them v1 up to v3n by their forward degree. So the v1 has the smallest forward degree, v2 has the next smallest, and so on. Right. So, and define, so we look at the first vertex, where its forward degree is at most 10 times its label. So I'll just draw you a picture. If I'm plotting v1 up to v3n here, and I plot their forward degrees on the y-axis, we know because the minimum degree is at least n plus tau, every vertex has at least tau neighbours in in the next part. So you start above tau. At the end, so it's increasing, this is increasing, and no vertex has more than n neighbours in the next part, which just isn't space. So this is what this looks like. If you plot 10 times the label, I'll shoot through here, and this is your vertex VK. So notice, okay, one thing to notice, K is more than tau, just because 10K is the height here, so that's at least tau. So K is pretty big, comparable to tau. And now, okay, let's consider Vj, where J is close to K, so between K/2 and K. Its forward degree is at least a forward degree of Vk/2, but by minimality of K, we know that the forward degree of Vk/2 is more than 10 times its label. So we've got a good number of vertices, right? K/2 vertices, so tau, forget about multiplicative constants, but tau vertices, all of which have big forward degree. So here's Vj, and it has 5k, at least 5k forward neighbours. How many of these edges are not boosters? If it's not a booster, so there's some vertex here, if that's not a booster, that means that V was before Vj in the ordering. Because literally, if you're later in the ordering, the forward degree goes up. So the number of non-boosters, the number of these forward edges that are not boosters, is at most the number of vertices that appear before Vj in the ordering. That's at most K. So all of these vertices have 5k forward neighbours, and most K of them are non-boosters. So they have at least 4k booster. And this is great news, because we have K/2 vertices. All of them are incident to 4k boosters, and every booster, I told you, creates tau triangles. So the number of triangles, at least this, maybe divided by 6 or something. But K is big compared to tau, so this is so you're getting tau squared boosters and lots and lots of triangles. But unfortunately, you do this lovely, but you don't get a very good bound when you end up. The bound they got was big O, n to the 1 minus 1 over 3t squared. And right, how do we do better? So your first thing is you might hope, oh, maybe we can get more triangles. Maybe we can be clever and get more triangles. That doesn't work because, in fact, Bollobás, Erdős, and Szemerédi gave examples where you can't get more triangles. So getting more triangles is no good. What you have to do is we need to have a structure for the boosters. We need to understand where are the boosters, not just like they live somewhere ambiently. We need some structure. And so our strategy is understand where the boosters are, and step 1 is we find 2 possible configurations. So we show that in our graph there must be one of the following 2 things. Option 1, a bipartite graph, not complete, but where all of these edges are boosters, and this is a dense bipartite graph. So its density is at least, let's say, 1 over 100. So it's a good, genuinely lots of edges here. And how big are the parts? The parts of size like at least tau. So maybe we're thinking t equals 2. So sort of square root, if we're thinking t equals 2 now, you're thinking square root of that.
So these vertices should be from the same parts.
Yeah. So part 1, part 2.
And there can be some other edges in between.
Yeah, I forget the other edges. What matters is I get the booster edges in here form a dense set of edges. Yeah. That's option A. Option B is more, it's harder to find, so maybe I will just, so you don't get density, but you get lots of vertices, each of which see lots of edges, and these are all, let me just call them super boosters. They're better than boosters. Let me not define them, but that's, I won't dwell very much on this. So this is sort of option A, option B, and first you show there will always be one of these two things. Then you have to work, right? And the style, just to give you a sense of the style of argument, because I think my time is almost up, is what I guess you would call it a, okay, let me put this in quotation, a density increment argument. Now, let me just sort of explain with reference to figure A, and it's not really density, it's not really increment, but let me explain. So you have this nice thing here. So, not complete, but nice density boosters. And suppose you also know that for every edge here, they have, so this is part 1, part 2, and the third part, they have at most d common neighbours. You just have a d is some number, it's a bound. Every pair have at most this. You show either you get the KTTT you want, or if you fail, you can drop to some sub-collection of these. So you don't, with slightly fewer edges, still they're all boosters. The density is a bit smaller, but still it's constant. So maybe if this was 1 over 100, maybe this is 1 over 10,000. The density's dropped a bit, but now, for every edge between here and here, the number of common neighbours is now even smaller. So d times n to the minus, sort of polynomially dropped. And then you iterate this. And at each step, either you exit, happy, you found my thing, or the codegrees drop. They can't drop forever though, because these are booster edges. Booster edges have at least tau common neighbours. They have at least sort of square root of n common neighbours. So actually, after a bounded number of iterations, you die, and you must at some point have exited. So really, it's a sort of codegree decrement, but it's of the flavour of density increment that's used to prove like Ross theorem or something like this. That's for A. For B, we do a similar style but very different. You optimise something else, another density increment, where either you find the KTTD, or you exit to option A, or you increase the density, and again, after a bounded number of iterations, you fail, so you must at some point have either exited, in which case you win, or won directly, in which case you win. Great. I think my time's up, but thank you very much for listening.